Hi there. In this video, we'll talk about slope field. A few things about it. Let a differential equation of the form y derivative equals f of x comma y, which means that we have a differential equation that expresses the derivative of a function y as in terms of x and y respectively. We know that y derivative geometrically shows the slope of function y at a certain point. Assuming now that we are given a set of points x comma y that lie on the graph of y, we can use the given differential equation to calculate y derivative for each one of them. That value, which is actually the slope at each point, can be now used to draw short line segments that indicate the direction in which the solution curve would move if it passed through that point. All of these slopes drawn for each one of these given points form a graphical representation that is what we call slope field. The slope field can help us in general to visualize the behavior of the solutions to the differential equation and can be used to estimate the shape of the curves without actually solving the differential equation itself. By analyzing the slope field, we can gain insights into the behavior of the solutions to the differential equation, such as whether they are increasing, decreasing, or even oscillating, and where they might have critical points or asymptotes. Right now, we will work together three different exercises. Let's move to exercise number 1. Sketch a slope field for the differential equation written by y derivative equals 1 minus xy for the given points, negative 1, negative 1, negative 1, 0, and so on. So, we need for each one of these points, and at first I will draw a set of axes and x comma y, x-axis and y-axis, and I will put all these points. Let's assume that here we have 0, 1, and 2, and here we have negative 1, 1, 2, and negative 1. So, at first, negative 1 would be this point over here. Negative 1, 0 would be that point. Negative 1, 1, negative 1, 2. Similarly, 0, negative 1 would be that. 0, 0, 0, 1, and 0, 2. And finally, 1, comma negative 1, 1, comma 0, 1, comma 1, and 1, comma 2. So these are the points for which we need to create a slope field. The next step, and let's call that step number 1, my next step, step number 2, would be to actually calculate y derivative for each one of them. To do that, it would be really helpful if I were to draw a table of values. We have the values x and y here. Let's put negative 1, negative 1, negative 1, negative 1. And by that we mean negative 1, negative 1, negative 1, 0, negative 1, 1, negative 1, 2, 0, negative 1, 0, 0, 0, 1, 0, 2, 1, negative 1, 1, 0, 1, 1, and 1, 2. Remember that I need to reach this expression here, 1 minus xy. So it would be also useful if I could draw a third line to represent the product between x and y. Negative 1 times negative 1 should be 1, 0, negative 1, negative 2, 0, 0, 0, 0, negative 1, 0, 1, and 2. And now I'm ready for the subtraction. 1 minus 1 is 0. 1 minus 0 is 1. 1 minus 1 should be 2. 1 plus 2 should be 3. 1 minus 0 should be 1, 1, 1, and 1. 1 plus 1 should be 2. 1 minus 0 should be 1. 1 minus 1 should be 0. And 1 minus 2 should be negative 1. Now, remember that each one of these last values, 0, 1, 2, and 3, represent slopes. So, in each one of these points, I will put small segments that actually represent these slopes. Let's begin with the easiest ones, which are these. A slope of 0 would indicate that we basically have a segment that is parallel to the x-axis. In which points do we need that? At point -1, -1, and at point 1, 1. So I should go to these points. -1, -1 is this point over here. And 1, 1 is this point over here. And in these points, I need segments that are parallel to the x-axis. So it could look like that and like that. Next, we have a slope of 1, which occurs in these points. Here, at point with coordinates -1, 0, here, here. So at this, that, and that points. -1, 0, it's this. 0, -1 should be that. 0, 0, 0, 1, 0, 2, and 1, 0. So in each one of these points, I should draw small segments that have a slope of 1. A slope of 1, remember that the equation y equals x has a slope of 1. So the slope of 1, let me zoom in so that you can clearly see it. A slope of 1 could be this. They could go like that, like this, like this, like this, like this, and like that. My next slope in terms of value is the slope of 2. This occurs at point -1, 1. -1, 1 is this point. In that point, I need to draw a segment that has a slope equal to 2. This should mean that that small segment should look steeper than the blue one. So I will simply do it a little bit steeper. Similarly, my biggest value is when the slope is 3, which occurs at point with coordinates -1 and 2, which is this point. I need to do the steepest slope of all, so I will draw it a little bit like that. And finally, at point with coordinates 1 and -1, no, at 1 and -1, I still have like the pink one, so it should be like the pink, it should be like this. But at point with coordinates 1 and 2, I have a slope of -1, which means that I should draw it like this. Look at that now. Imagine it without the highlighted colors, and there you are. You have the slope field that you needed. So if in case you are given a set of points and the differential equation, and based on that differential equation, you need to create a slope field, you'll do it in 2 simple steps. At first, you'll draw a set of axes, if it's not already there, on which you'll plug in, you'll put your given points. Then, for each one of these points, you will create a table of values, and step by step, you will create the given differential equation. Remember that you care for the slopes, and remember that by slopes we mean the value of y derivative. Once you found it, you should keep in mind that these values represent slopes of small segments. You draw them, and you have the needed slope field. Let's move in another exercise. In this case, you are given a slope field and 4 different options. which one do you think, which one of these options do you think that could describe that slope field? Remember that it's all about values. So, what can we see? Let us see that here in first quadrant, we know that for a random point xy, both x is positive and y is positive. So, let's take chances. Assuming that in the first quadrant, it was, and all slopes also are negatives. Could it be A? No, because based on A, we would simply have the division between x and y, which are both positives. So we would expect positive slopes. So A is rejected. Could it be B? Y derivative would have been x squared over y, which is positive over positive, which is still positive. Rejected. We see that we have negative slopes. Could it be C? Based on C, we would have minus x comma y, which is minus a positive over a positive, which in the end is a negative one, which is maybe. It could be C. Could it be D? Y derivative is minus x squared over y, which is minus something positive squared over positive, which in the end is negative. So once again, maybe. It's a good thing because we have already rejected A and B. How can we reject more? Let us use this time the second quadrant. In this quadrant, we know that x values are negatives and y values are all positives. But we also see that each one of these small segments have a positive slope. So slopes are all positive. Now, remember that we are left with two options now. It's either C or D. Let's work each one out. In C, y derivative, which is minus x over y, would have been negative. X is also negative. Y is positive. So we would expect to have minus, minus. So it should be positive, which means that maybe it's this one. Could it be D? In D, y derivative is defined as minus x squared over y, which is minus squared over something positive, minus positive over positive, which is minus. No, it cannot be. Rejected. So my solution is C. C could actually be the differential equation describing the slope field we have in front of us. And finally, let's see the third exercise, which kind of looks like the second one. The slope field represented below could be the slope field of one of these. What should we do here? In the second one, look, in each quadrant, we knew that we used to have the same slope in any of the points of each quadrant. For example, in the first quadrant, we could clearly see that we would have negative slopes. In the second quadrant, we would have positive ones. In the third one, we would have negatives. In the fourth one, we would have positives and so on. Here, however, in the slope field presented, that's not the case. We can see that there are values in first quadrant that end up at a positive slope and some others at a negative one, respectively. What should we do here? We could be more specific and work with points instead of random x, y coordinates. What do I mean about that? Let's go here. Let me use a different color. Let's go here in this point, which is point with coordinates 0, 2. I can see that at 0, 2, the slope is positive. So I can take these coordinates, x and y, plug them in each one of the 4 possible answers, and see what happens. In A, for instance, y derivative is 0 squared plus 2. It is 2. It is positive, so we could say that maybe it is A. In the second one, y derivative is minus 0 plus 2. It's still positive, so maybe. In C, its y derivative is 0 plus 2 squared. It is 4. It is a positive, so once again, maybe. Perhaps this point doesn't help us that much. In D, y derivative is x squared minus y, which is 0 squared minus 2. It is negative, so there you are. We should reject one. We should continue, however, with another point. Let us use this point here, which is the point with coordinates 2, 0. And here we see that at this point, slope is negative. So let's try and plug these coordinates in the left 3 cases. A now gets 2 squared plus 0, which is 4, which is positive. Therefore, it has to be rejected because we can see from the slope field that it should have been negative. So A is rejected. In B, y derivative is minus 2 plus 0, which is minus 2, and it could be that. In C, it should be minus 2 plus 0 squared. It is minus 2, so once again, maybe would be there. 2, 0. So from that, we have rejected A. What should we do next? Let us use now this point. It's the point with coordinates 0 and negative 2. We can see that at this, at 0, negative 2, slope is negative. So we are left with B. Y derivative is minus 0 minus 2. It's minus 2. It is negative, so we could say that maybe it is that. At C, y derivative should have been x plus y squared. Here we have 0 plus negative 2 squared. That is equal to 4. It should have been rejected. So we are finally left with our solution. The solution in this case is B. The differential equation y derivative equals minus x plus y could be the differential equation representing this diagram. And that was all. I hope I helped with this video. Remember that exercises on slope field are not extremely hard. We will be given either the points and we will be asked to represent the corresponding slope field, or we might be given a slope field and we will have to choose between different options. That was for the moment. If, however, you feel that you face any difficulties on what you just saw, you are always free and welcome to leave your comment below the video. As always, thank you for your time.